Hello, ladies, gentlemen, and in between, and welcome back to another episode of Maths with Hamblin with your beautiful host, Hamblin. And today, my boys, we're just going to be looking at the conditions for lines in the xy plane to be parallel or perpendicular. It's going to be pretty nice and fun, and a nice little derivation halfway through. Let's have some fun. Let's go. Okay, so the first case we're going to look at is when two lines are parallel. So, what could be the condition for two lines to be parallel? Well, when you look at it, you might intuitively and correctly assume that their gradients must be the same, because if you recall, the gradient is kind of a measure of how steep a line is. A more steep line, bigger gradient, a less steep line, a lower gradient. And every single line has a unique gradient, and every unique gradient specifies a unique amount of steepness. So because two parallel lines are by definition the exact same amount of steep, and they'll never meet each other, then that means their gradients must be the same. But how do we prove this? How do we prove this rigorously and definitively? Well, take a look at this. Let's calculate the gradient of this lower line down here. So all we need to do is take a step in the x direction and a step in the y direction, and make sure that we meet back with our line, and divide this length by this length to get the gradient. Now, because these two lines are parallel and have the same gradient, the only difference between them is that they're shifted up or down the y-axis. They're just shifted versions of each other. So if we can just map this line perfectly to this line by just shifting it up. So if we just shift this line up to this line, we're also going to shift this little triangle we've drawn up. And because shifting a triangle doesn't change the dimensions, it doesn't change the ratio between the sides, we can say that when you divide this by this and this by this, you must get the exact same number because they both are in the same dimension with each other, because they're just shifted and translated versions of each other. Now, isn't that easy? The condition for lines to be perpendicular, however, are a lot more interesting. Let's have a look. Okay, so let's examine the case where we've got two lines in the xy plane that are perpendicular to each other, meaning that when they cross each other, they cross at exactly 90 degrees, indicated by this little square here. So, in order to prove they're perpendicular, first what we're going to do is draw a triangle with this first line and compare it to the triangle we can draw with this second line and seeing what we get. So, anyway, if we draw a little triangle for this first line, let's just say that this length here is some x and this length here is some y, then the gradient of this first line, which I'll call m1, is literally just equal to y divided by x, as you should know already. But you can think of these two lines as just 90-degree rotations of each other. Because they meet at a right angle at 90 degrees, you can just take this line and flip it 90 degrees and you'll get the exact same line, as long as you flip it about this point, as in imagine fixing the intersection point and then rotating it. But what that means is if you rotate this triangle with it, imagine fixing this point in place and rotating this triangle around 90 degrees, because these two lines are 90-degree rotations of each other, this triangle will also carry over and copy itself, and you'll get the exact same triangle again. It may not look like the exact same triangle, but that's because I'm not very good at drawing. Anyway, so now, because we've just rotated, we haven't changed the lengths, this y in the y direction, this length here is just going to be x, and in this direction here, the length will be y, but remember, we're going to calculate the gradients. So because this step is to the left, we should count this as negative, so this will be negative. Take note, you can clearly see that this and this are positive, so negative y will indeed be a negative number. So we know the gradient of m1 is y over x, but what's the gradient of m2? Well, we're going to need to do its change in y divided by its change in x, but m2, its change in y is x, positive x, and its change in the x is exactly negative y. But look what happens here. Now let's see what happens when we multiply these two, right? I mean, they're basically flipped versions of each other. So if we multiply them, m1 times m2, that will equal, well, y over x times x over negative y. That will cancel all the way down to negative 1. Now look at that. Isn't that amazing? We've shown that two lines that are perpendicular, because of the fact they're a 90-degree rotation of each other, that their two gradients must multiply to negative 1. So that is really helpful. So if you know the gradient of one of these lines and you want to figure out the gradient of the other one, all we need to do is plug it into this equation and you can easily figure it out. Now, isn't that cool? I just love maths. Anyway, let's do some practice problems. Okay, so this first problem goes like this. line L1 has equation 2y plus 6x equals negative 2, and line L2 has equation 3y plus 9x equals 15, and we're asked to show that L1 and L2 never intersect each other. Now, the condition for line L1 and line L2 to never intersect each other is that they must be parallel, as you learned last time, because remember, if they're parallel, they have the exact same gradient, and they'll never meet each other, but even if they're just a little bit not parallel, then they'll eventually meet each other because, you know, the xy plane is infinite. So all we need to do to show that L1 and L2 never intersect is to show they're parallel, and you know now to do that we need to show that they have the same gradient. But how do we get the gradient from these two equations? Well, we just need to rearrange for y equals blah 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 and read the coefficient of x. So let's do this first one. So let's say we just move the 6x over to the other side. So we get 2y equals minus 6x minus 2, and then we divide by 2, and then we get that y equals negative 3x minus 1. So L1 has gradient negative 3. Let's check for the gradient of line 2. And we'll hope that it's negative 3, and then we'll have shown that the lines are parallel. So moving the 9x over, we get 3y equals negative 9x plus 15. Bada bing, bada boom. Divide by 3, you get that y equals negative 3x plus 5. So L1 has gradient negative 3, and line L2 has gradient negative 3. And because they have the same gradient, this must imply that L1 and L2 are parallel. Therefore, they must never intersect. Done. Okay, so this second problem is a little bit harder than the first. It goes like this. Line L1 has equation y equals 5x plus 1 and is perpendicular to another line L2, and they intersect at the point 316, and we're asked to find the distance between the x-intercepts. Okay, so good problem-solving strategy. Unpack all that information clearly. So L1 has equation this, so we know its gradient and its y-intercept, and it's perpendicular to L2. So, as we've learned previously, that must mean that L2's gradient multiplied by 5 must equal negative 1. Very useful information. We can use that to figure out L2's gradient. And we know that they intersect at the point 316. Okay, useful, okay. And we're asked to find the distance between their x-intercepts. And their x-intercepts are the points where the lines cross the x-axis, which, if you remember, that's where they must have a y value of 0. So that's also useful information. Now, we've got to figure out how we're going to do this problem. And if we're going to figure out their x-intercepts, we're going to need to know both lines, gradient and y-intercept. In other words, we're both going to, English language, we're going to need to know both of their equations. So we know line L1's equation, but how are we going to figure out L2's equation? Well, as mentioned before, we can easily get its gradient. We know that the gradient of line 2, which I'll call m2, times by 5 equals negative 1. Therefore, the gradient of m2, the gradient of line 2, is equal to negative 1 over 5. So that's fantastic. Okay, how are we going to find the y-intercept though? I mean, we need the y-intercept. Well, fret not. We know that the two lines intersect at 316. And obviously that means that line 2 passes through 316. So what that must infer is that 3 and 16 must satisfy the equation of line 2. In other words, if we set up y equals minus 1 over 5 x plus c, we can plug in 3 and 16 and solve for L2's y-intercept. So, in other words, that means 16 must equal negative 1 over 5 times 3 plus c. That simplifies to 16 equals negative 3 over 5 plus c, and then we just need to add 3 over 5 on both sides, and then we get that c equals 16 plus 3 over 5. Oh, that's not going to be a nice number. Anyway, let's just rubber this bit out so we can combine those fractions real quick. So there we get that c equals 16 plus 3 over 5. Common denominator, multiply 16 by 5, so we get c equals, what's 16 times 5? That's 80 over 5 plus 3 over 5. In other words, c is 83 divided by 5. Brilliant, so now we can write the equation of L2 as y equals negative 1 over 5x plus 83 over 5. That is a horrible, horrible equation. But anyway, now we know the equations of both lines, and so we can solve for their x-intercepts. Whew. Anyway, how do we solve for the x-intercepts though? Well, we know that at the point of x interception, that the y-coordinate at both of those points must equal 0. So all we need to do is take the equations of both lines, set y equal to 0, and find out what x has to be. Doing that for line L1 first, we get 0 must equal 5 times x plus 1, or in other words, x equals negative 1/5. Doing that for line 2, that's 0 equals negative 1 over 5x plus 83 over 5. So we add 1 over 5x on both sides, and then we multiply by 5, and then we get that x equals 83. Golly gosh, that is a big and random number. Amazing, right? And now all we need to do is find the distance between these 2 points. Well, what's the distance between negative 1 over 5 and 83? Well, if you think about it, it's going to be 83 plus 1/5. So, unfortunately, we have to combine one more fraction, and then we'll be done. 83 plus 1 over 5. Okay, 83 times 5, 415 over 5, plus 1 over 5, and we get that the final distance is 416 over 5. You are free to decimalize that as you wish. Actually, easy, it's 83.2. The distance is 83.2. Anyway, that's all I have for you today, my friends. I hope this video was very helpful, and I hope it was very cool to see why two gradients that are perpendicular must multiply to the negative 1. I found that very satisfying when I first arrived at. Anyway, that'll be all for this video. I hope you have some fun watching this, and I hope you have some fun with the rest of your day. Next episode, we'll be deriving the equation of a circle. Have fun, guys. Capiche?